This is part 2 of my fractal market analysis series. I'm not quite sure how many parts there will be to this series, but if you watch the first video, which I'll link below, this is based on a book by Edgar Peters called Fractal Market Analysis, and he's basically applying fractal analysis, which is a thing separate from markets, and chaos theory to analyzing markets. This book is from the 90s. It's been around for a while, but if you go on places like Investopedia or any other website that kind of teaches you economic analysis or just investment theory, this is like the esoteric stuff that you just stumble upon, and I found it super interesting, so that's why I'm doing it. So yeah, in this part, in part 2, we're going to be looking at what a fractal is and how it relates to chaos, because chaos is kind of tied up into fractals, and we're going to look at complexity, and then we'll finally tie it all off by kind of defining how this applies to what we're going to be looking at with actual fractal market analysis. So honestly, I think this is going to be the funnest part of the video, but also the most challenging because, or the series, but also the most challenging because it's hard to define. Like, there's no standard definition of a fractal, so it's kind of something that you have to understand conceptually, which is great, and that's kind of fun in its own way. It's just, again, I'm not an expert, so it's hard to navigate these topics without a strong guide. So I did my best, and I hope it's interesting. So the first thing, we're gonna split this up into 2 parts. We're gonna introduce what fractal space is, and then we're gonna talk about fractal time. Now, when we talk about markets, we're talking about fractal time. So these aren't the fractals that you're used to, but they are statistical fractals. But it's important to understand what a fractal is before we even talk about what a statistical fractal is, So I give a few examples. We're going to talk about human lungs, the Sierpinski triangle, and the logistic map. Honestly, there are so many examples, and a lot of them, or most of them, I don't think I've come across one that doesn't tie into chaos, which we're also going to talk about. And there's a few things like Euclidean space, recursion, self-similarity, power laws that we need to define in order to get a better grasp of what a fractal is. And fractal dimension especially, just as a heads up, is going to be super important when we talk about fractal market analysis, because it's really like the fractal dimension of a fractal is how we can quantify how much of a fractal it is. It's really important. And then we talk about complexity just because I have to mention it in another part of the definition. So again, all of these, I'm just going over all of these. I'm not necessarily, we're not going super in depth, but this is stuff that interests me a lot, so I can see myself making more in-depth videos. There's some stuff that I really wanted to get into. I wanted to talk about the Mandelbrot set and Julia sets, and I wanted to talk about the Lorenz attractor and stuff like that, but it was too cluttered, so we'll just move on. So when we think of fractals, we normally think of, you zoom in and you get another thing that looks the same as what you zoomed in on. So I have a video here. So this is, when we think of fractals, I think this is normally what we think of, and this is the Mandelbrot set. So this little Buddha-looking guy is what we think of, I think, because this was the defining fractal. This was what Mandelbrot really kind of explored in his book, which I forget what it's called. It's kind of embarrassing, but that's okay. So yeah, I think you get the basic picture. You zoom in, but actually something I want to mention is, you're zooming in, but you don't see the same object at all scales in this fractal. And so we will talk about this later, but it's not exactly the same as itself the more you zoom in. There are some fractals where that is the case, but most fractals you see in nature aren't like that at all. And that's kind of the same with statistical fractals, so that's important to mention. The other thing about fractals is that they are recursively defined. So I will explain this again, but let's say you have a variable x and then you have a function of x, okay? Then recursion would be taking the result of putting x into f of x, the function of x, and putting it into the function again. And then you take that result and you put it into the function again, and again, and again, and again, and again. That's basically what recursion is. But I'll show you. Fractals scale according to a power law, y equals ax to the b, where b is not necessarily an integer, and b is called the fractal dimension. So with fractals, it's usually not an integer. Actually, I can't think of one where it is an integer. Again, I'm not an expert, so. So this basically means that fractals exist between dimensions. So for example, when we talk about random walks, a random walk has a dimension of 1.5, because you can think of it as there's a 50-50 probability of a random walk, filling 2D space or being a one-dimensional line. And that's where, when we saw that Brownian motion trajectory graph in the previous set of videos, or the previous video, it was all kind of like rough and jagged. And so it's between 1 and 2 dimensions. This means that fractals are a subset of Euclidean space, and we will talk about what Euclidean space is. I just think this fact kind of makes it more concrete that fractals exist where we exist. There's not some other like esoteric space defined for fractals. They're where we are. In fact, a wiffle ball, like the ball where there's a bunch of holes in it, so it's really light, that exists between dimensions. It's not quite a third-dimensional object, and it's not quite a two-dimensional object. It's kind of in between there. So yeah, fractals exist in that kind of ambiguous space as well. It's not really ambiguous, but you know what I mean. The other thing about fractals is that they're nowhere differentiable. If you've taken calculus, you'll know what this means. But just in case you haven't, I'll try and give an idea of differentiability now. So I will just draw 2 graphs. And label the axes like a good girl. Okay, so I'll just draw 2 functions here. And we'll call this one f of x, and this one is g of x. So when we talk about a derivative, so if something is differentiable, it means you can take the derivative everywhere. And we'll just say that the derivative is the tangent line at a given point. So say you want to find the tangent line at this point here on the graph. Now it's only defined for one point. When you take the tangent line at that point, it should be defined everywhere in order for a function to be differentiable. The derivative, so the tangent line, has to be defined everywhere, but you only take it for one point. So in this case, we'll take the tangent line here, and it's just going to kiss that point right there. And on this graph, it looks like it's touching other points, but theoretically, it should only be touching this one point. And because of that, it's going to have a well-defined slope. And the slope of the tangent line is what we're going to be taking as our like derivative. But for a function that's not differentiable, so this function isn't differentiable because if you have a point here, if you want to take the derivative at this point, you can't, because on either side of that point, you have like the function just goes straight down. So the tip of this kind of like triangle here, that's just one point at the very top of the triangle. So if you try and take a tangent line there, like where are you going to put it? Because you could put it here, but you could also put it here, but you could also put it here. So you can pretty much put it wherever you want. So really the tangent line doesn't have a slope. Like it doesn't have a slope right there because it could be any of these slopes. So you can't define the tangent line for a really rough looking function like this. And that's kind of what a fractal is. A fractal is so rough, it basically, it's differentiable nowhere. It's so rough that it always looks like this because it always has an infinite amount of detail. It's so rough. All of these points are like this, basically. Another thing about fractals, which is probably the second most well-known property of fractals, is that they're self-similar. But there's different kinds of self-similarity. So as I was explaining with that zooming in video, where we were zooming in on the Mandelbrot set, that wasn't exactly the same at each zoom level. There's different pieces to the Mandelbrot fractal. And so you will have some fractals that are exactly self-similar, and you'll have some that are statistically self-similar, and some that are statistically self-affine, which is what a fractal time series is. It can only be statistically self-affine, and I will explain what that is, but just to understand that there's different kinds of self-similarity, and it doesn't always mean that the fractal looks the same on every time you zoom in. We can also say that a fractal is chaos in space, and this is the most fascinating property to me. So we will define chaos in a little bit, but chaos on a basic level means local randomness, but global determinism. So there's a chaotic system. When you look at it on kind of a detailed level, it looks kind of random, like there's no discernible pattern. But then when you zoom out, it has a structure. It has something that you can define as structure. So it's globally deterministic, but locally very random. And that's kind of what chaos is. So chaotic processes give fractal geometry when mapped graphically. And we'll talk about that when we look at the logistic map and the Sierpinski triangle. Right, so the fractal in this case would be called the attractor of the chaotic system, which is just kind of, it's kind of where, like the attractor is that structure kind of where values in the system orbit, so to speak. The fractal image is a visual representation of a strange attractor or repeller that defines the orbit of a deterministic system that behaves chaotically. So I'll illustrate how chaos is related to fractals with the chaos game. And eventually this is going to construct the Sierpinski triangle, which looks like this, okay? So how this works is you draw the three vertices of an equilateral triangle, and you label them in three different ways. So in this case, we've got three different colors. And then you pick a random point anywhere on the page. It could be inside the triangle, it could be outside the triangle. And in this case, the game randomly assigns that point a color. And the vertex corresponding to the color of that dot, you draw a line halfway from that dot to that vertex, and you put another point there. And then you just keep doing the same thing over and over and over again. And so that's what's happened here. And you can reset this and do it as many times as you want. And these first dots, these first 10 dots, they're always going to look different. They're always going to be in different spots because we always start off with a different dot. This isn't the dot that we're starting off with, by the way. Right? But then at the end of it all, you always get, like, the more dots you draw, you will always eventually get the Sierpinski triangle. And this is a perfect example of how chaos relates to fractals. We have this random process. It's initially random. So when you look closely, like for example, when you have what is this, like 30 dots here, it looks random. It looks like they're randomly placed. But then globally, on a global scale, it has this structure, and you find that the reason it has this structure is because by the process of the game, the way that the game is set up is a dynamic system. So the points that you draw will never, ever, 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 ever end up in these white spaces. They will never end up in those spaces. And that's the attractor. That's why this fractal is an attractor, because all of the points, just because of the way that the system is, end up on the Sierpinski triangle. So the Sierpinski triangle itself is an attractor of a chaotic system. So now we'll define Euclidean space, just because it's kind of important to understand the sort of space that we're talking about. Previously we said that fractal space is a subset of Euclidean space, and this is our buddy Euclid right here. This is defined for geometry, which is important to mention because sometimes we have spaces containing non-geometric objects, since spaces are just sets with structure. So we are talking about like a geometric kind of space here, a space in which geometric laws apply, which is why we can do certain types of analysis on fractals. So Euclidean space can be thought of as a model for physical space. For example, volume is a property of a third-dimensional object in Euclidean space, which is measured with 3 orthogonal variables in the same units. So instead of an xy axis, you have another orthogonal axis like that. And with these 3 units of whatever object you're measuring, you can get its volume. For example, 3 times the side length of a square equals its volume. You can also define Euclidean space as the space in which the axioms and notions of Euclidean geometry apply. So Euclid just made all of these axioms to define what you could do in Euclidean space and what it is. And it's basically just kind of what you'd expect. You can draw a straight line from any point to any point. You can describe a circle with any center and distance, and et cetera, et cetera, et cetera. You can pause the video if you want to see all of these. So now we'll talk about recursion, and the picture I'm using for this particular slide is a perfect example of recursion. So you start with a seed, you would call this your seed, and then on every piece of that seed, you put the same seed. So you can see that on this arm, you have something that looks like the original seed, and you just do that over and over and over again, and you make this beautiful tree, which is also what we saw in the introduction tree. This is a fractal as well, and I made a little video to kind of show how this works. So my seed is just that kind of forked tree, and then on each branch, I just draw another fork. And when we talk about a fractal, we're talking about the limit of that process. So I stopped here, but a true fractal, the process keeps going and going and going and going and going. So this is only a a representation of a fractal. This isn't a real fractal, if you know what I mean. It's just that I don't have the resources to go all the way to the limit. And this is why you can zoom infinitely on the Mandelbrot set, is because the Mandelbrot set is a limit. The fractal attractor of the Mandelbrot set is defined by a limit. You're taking the process to its limit. So now we'll talk about self-similarity and the different kinds of self-similarity. And this image is called the Sierpinski cube. So it's like the Sierpinski triangle, but it's in 3 dimensions and it's a cube. So previously we said that fractals are self-similar, and all fractals have some kind of self-similarity. There are different types of self-similarity. Most fractals, i.e. those found in nature, don't have exact self-similarity. We can best describe many natural objects as being statistically self-similar, which is how we'll also look at markets. In exact self-similarity, the fractal appears identical at different scales. Fractals defined by iterated function systems often display exact self-similarity. So this is the Sierpinski triangle that we saw with the chaos game, and there's also another set of slides for the Sierpinski triangle, so I can show you exactly what I mean by an iterated function system and exact self-similarity. Quasi-self-similarity, and this isn't exact self-similarity is kind of well defined, but quasi-self-similarity, it took me a while to find this term. So again, when we talk about fractals, there's not a black and white definition as with most things in mathematics, and that's because fractals are just, you can't really contain them, and that's why they're so fascinating. So in quasi-self-similarity, the fractal appears approximately identical at different scales. It contains small copies of the entire fractal in disordered and degenerate forms. So this is what we see in the Mandelbrot set. Fractals defined by recurrence relations are usually quasi-self-similar, but not exactly self-similar. An example of this will be the logistic map, which we'll talk about in a little bit. Statistical self-similarity is what we'll be focusing on for the remainder of the series after this video. So the fractal has numerical or statistical measures which are preserved across scales. Most reasonable definitions of fractal trivially imply some form of statistical self-similarity. So most fractals are statistically self-similar, even if they're exact and quasi-self-similar. So fractal dimension itself is a numerical measure which is preserved across scales, and I think I mentioned that the fractal dimension is a way that we can quantify how much of a fractal is. Random fractals are examples of fractals which are statistically self-similar, but neither exactly nor quasi-self-similar. And mentioning that is just kind of for your own benefit. If you want to look up what a random fractal is to help you better understand statistical self-similarity, you can do so. I do mention it later on in the slides. So most fractals are not scale invariant. And if something is scale invariant, it means it will look the same at different scales. But most fractals aren't scale invariant. They look different at different scales. So if you do your own research on fractals, you'll come across this term quite often. So fractals with exact self-similarity are scale invariant, and they kind of mean the same thing. If a fractal is scale invariant, then it is exactly self-similar, basically. And this is an important property. A fractal is equal to itself typically for only a discrete set of values, for example, the logistic map. And the property is important for markets because when we look at the data later on, the actual data for market returns using indexes like the Dow, we'll see that for certain values, these markets show self-similarity and then they quickly stop showing self-similarity, which is pretty interesting. So that's a pretty important property. And again, we'll look at the logistic map in a little bit to kind of show you what that looks like. And then self-similar objects are described by a power law. So when we say that fractals are described by a power law, this is because they're self-similar. So not all self-similar objects are fractals, but every self-similar object, including fractals, are described by a power law, and I will explain that as well. So I think I'll end the video here. We're at about 22 minutes now, and I'll start off with power laws in the next part, in the next video. So I'll talk about why self-similar objects are described by power laws, and thus why fractals are described by power laws. But I wanted to end this with a quote that I got from a paper, which I'll link in the description below, but this paper kind of goes into a similar realm where it's trying to explain what the relationship between power laws and self-similarity and fractals is, but there was a lot of just really poetic, kind of meaningful statements in there. So this person said, in self-similarity, similar patterns are repeated with different sizes or timescales without changing their essential meaning. Similar geometric patterns are repeated at different sizes and are expressive of a fundamental unity of the system. This is essentially why I'm so fascinated with fractals, and why pretty much everyone is fascinated with fractals. I haven't met a single person who said, I hate fractals. Everyone loves fractals. They're cool. You can extend this, they're expressive of a fundamental unity of the system. You can express this to spiritual topics, or you can extend this to spiritual topics, which I won't because this isn't a spiritual series, but I don't know. For me, that just expresses exactly why I like this stuff. So yeah, I'll see you in the next video, and we'll start on power laws and hopefully finish up the rest of the slides without making a part 4. So I'll see you in part 3.